So is it okay now?
Okay, no, it's still in. Here we are.
Okay, yeah.
Oh,
I
great,
think
perfect.
it's okay
Okay,
now. Okay.
so now it's perfect. So we hear you. So the stage is yours.
Okay. Hello, everyone from Perth, Western Australia. Thank you, Marcus, for the introduction. Yeah, my name is Amir. I'm from Genesis Span Group, and today I'm going to talk about precise orbit determination as a requirement of the LEO-PNT systems. Let's start with this fact that we all know that PNT using only GNSS is challenging, especially in the urban area. So we have some good signals from GNSS, but some signals, or let's say a lot of signals, are blocked, and we have also some signals that are reflected because of multipass. So the positioning accuracy will be reduced because of these problems that GNSS has in these environments. We also may be under attack of spoofers and jammers. So we have issues because of all of them. But at the same time, what we are seeing is that we have a lot of satellites in the LEO region, which is basically from 500 to 1200 kilometers. So I really like this this screenshot from LEO Labs, which shows all available payloads in the LEO region. So now the question is, how many satellites is available now, and can we use them for LEO-PNT or not? So the number of satellites that are available now, the major LEO constellations, we can add them up, is around 8,000 satellites in the LEO region. But we know that it's only the current satellites. We know that it will be extended to more than 60,000 satellites probably by 2013, and that is what we call it space proliferation. So, but all of these satellites, no matter they are broadband constellations or they are dedicated satellites for LEO-PNT, they can help us to augment GNSS, or they can act as a dedicated positioning, navigation, and timing system. So the GNSS community actually brought this term LEO-PNT systems. I think the other two speakers mentioned all of the details about that. And what we are doing in the future PNT system, let's say a space-based PNT system, is developing the models, no matter it's from the satellite side or the user side. From the satellite side, it's basically about orbit determination, and from user side, it's basically about positioning. So let's start with the satellite side. So why actually we need to know the exact location, or let's say the position or the orbit of the satellite, of the LEO satellite, with high accuracy. Why? Because of if you look at the basics of the satellite-based positioning, if we have ranges between satellites and the users, we can perform positioning. That's the basic idea. So what's the known information for us is the satellite orbits and clocks, which is coming from the orbit determination step. So we know that more, or let's say higher orbital accuracy brings higher positioning accuracy for us. What we need to do for the LEO satellites to do the orbit determination with high accuracy, we call it precise orbit determination, or POD. So we are talking about when we say POD, we are talking about the orbital accuracy at several centimeter levels, very close to what we have currently for the GNSS. So let's see how we can do POD for the LEO satellites. There are actually two main methods: kinematic POD or reduced dynamic POD. The kinematic POD is based on precise point positioning in the kinematic mode, meaning that we have some sensors, we have GNSS sensors on board the satellites, and then we can perform positioning for when the GNSS data is available at a specific time. So it's obvious, as you can see in the figure, it's obvious if we have the observation, we can determine the position, or we can have the orbit. Otherwise, we cannot have. And the other thing is that we can, the kinematic POD is very sensitive to the outliers and to bad observations. If the bad observations are there in the POD, so the orbital accuracy is not that good. Besides kinematic POD, we have a more accurate method, which is called reduced dynamic POD. The reduced dynamic POD is based on solving the equation of motion of the LEO satellite. It is basically solving the equation of motion by considering all the dynamic models that we know for the LEO region. But because some gravity part of those models are not that perfect, and there are some model deficiencies there, we are going to integrate GNSS observations and try to improve the orbit determination used in the reduced dynamic mode. Also, we are going to estimate some stochastic accelerations in the POD. So what is the output for this model is the continuous and more accurate orbit. But of course, that's, it needs a lot of processing. Now, the question is, no matter which method, when we are going to do it for the LEO-PNT system, is it going to be on a ground station for post-mission POD, or it's going to be everything on board or real-time POD? So I'm going to talk about them and mention the challenges that are available for each of them. So let's start with the post-mission POD. The assumption here is that we can have access to onboard GNSS observation, which is collected by the LEO satellites. So the ground station can receive those observations, will apply the GNSS orbits clocks, Earth orientation parameters, and there are different screening steps, and the output, and also the stochastic accelerations, estimation, and so on. And the output is a dynamic orbit, a reduced dynamic orbit, which it should be high accurate, meaning that it's the accuracy is better than 10 centimeters. It should be validated, and then it will be broadcast to the user, no matter through internet or the space link. Now, the user has the precise orbits of the satellite, of the LEO satellite, which is actually in near real time. So the user should apply the orbit and clock prediction. Okay, so what we have for the orbit is, let's say, precise orbit determination is applied for different remote sensing missions, as you can see, CHAMP, GRACE, GOES, and so on, and by different people. And you can see the accuracy that is achievable is better than 10 centimeters. No, even for the CubeSats, we reach to better than 10 centimeter of orbital accuracy. So that's very good for, conceptually for the LEO-PNT, and we can do the prediction for the LEO orbits, but there is an issue for the clocks. So again, the output of reduced dynamic POD, or let's say reduced dynamic POD, is the orbit velocity and clocks. So the orbit and velocities, or the orbital, or let's say position and velocity, are fine, but the clocks is depend on the type of the clocks that is available on board the satellite. So if the satellite is not equipped with an ultra-stable oscillator or an atomic clocks, so it's not stable enough for the prediction. That can cause a problem for us. As an example, in one of our studies, as you can see, the clocks for the CubeSats, which are mainly oven control crystal oscillators, are not stable enough. This figure shows the short-term stability of the clocks, and if we want to use them for the LEO-PNT, and if we want to predict them, it's not that good. So we need to estimate them time to, at each specific time, which increase the amount of processing and so on. So as you can see, there are some issues for the post-mission POD. Now let's move on to the real-time, or let's say onboard LEO-POD. When we say onboard POD, it meaning that everything should be done onboard. So the whole POD is done there, and then the output, which is the orbit and clocks of the LEO satellite, will be transmitted to the user through the signal. But there are some challenges there. One of them is that to perform POD, we need GNSS correction in space. The other thing is that usually the small satellites has limited power and processing budget. The other thing is that most of the small satellites are, or let's say broadband satellites, or CubeSats, they are equipped with commercial off-the-shelf sensors. So the quality of the sensor is a question there. That can cause a problem for the orbital accuracy that we need to achieve. And also, there are possibilities to improve using inter-satellite links that I'm going to talk about it in the following slides. So let's start with the GNSS corrections in space. Now, currently, we know that Galileo has, or high accuracy service provides this GNSS orbital and clocks corrections in space for most of the world. And as you can see, beside that, we have in Australia something called Southband, which is actually a service to provide GNSS clock and orbital corrections to the users. Beside that, we have other space links that provide these corrections, like Maduka from QZSS or the other commercial companies that provide in this service. The combination of all of them is showing in this slide. As you can see, for a satellite which is orbiting around the Earth in the LEO region, it is, if you consider the LEO constellation and Southband or the QZSS, during the orbit, we can have, for 1 day during the orbit, we can have always the GNSS corrections in space through the space link. So that is not actually a problem. The other issue that we have, or the other challenge that we have for real-time LEO-PNT is the limited power and processing budget. What is happening for the small satellites, as Eldar mentioned, for example, for the CubeSats, they are small, so they need to do something called duty cycling of the power. It means that the amount of power that we have on board a satellite should be rotated to different sensors, meaning that the GNSS observation or the GNSS sensor could be not available at all the times. It can be available at 40% of the time, or even the GNSS observation are stored with lower sample intervals. What will happen if we want to do with that type of data? We actually tested such things for and applied the reduced dynamic POD using the space links through Southband and the other available space links like QZSS, Maduka, and we reached to this level of accuracy. So yeah, in the reduced dynamic POD, we can have the orbital accuracy at around 10 centimeter or better than 10 centimeter, which is useful for LEO-PNT. The other issue is that the other finding is that the kinematic POD, as I mentioned, is very affected by the quality of the data and the amount of data that we have. You can see the red dots here are showing the kinematic POD with the same scenario, and compared with the reduced dynamic ones, you can see the orbital accuracy increased to around 2 decimeter level, which is not that good for the LEO-PNT system if you are talking about comparing with GNSS or as an alternative to the GNSS or augmenting GNSS. So the other challenge is the commercial off-the-shelf sensors. Now, people mentioned about different constellation, different LEO-PNT systems that are going to be up there. If the sensor quality is not that good, that can affect the orbital accuracy, and that will affect the LEO-PNT. For example, the attitude determination of a satellite. The attitude of a satellite is the orientation of the satellites in space. That's very important for precise orbit determination. What is happening for small satellites is they are equipped with magnetometers and sun sensors, which are not that perfect. Or, for example, sun sensors are work only in sunlight. If they are equipped with the star tracking, that's very good. They are very perfect, but the price is an issue if you're talking about thousands of satellites. And the weight of that sensor is a question for a small satellite like CubeSats. So what could be the solution? We provided a solution. We worked on something called an array of GNSS antenna, which is considerably lighter to any of those sensors, which needs less power, is very cheap, and by the model that we developed, we can reach to a good and acceptable accuracy. The model is here. I don't want to explain it here. That's called array-aided precise orbit and attitude determination, and it's published in Navigation. So if you want, you can check it the paper later on. But the outcome of that model and that scenario is if you look at the left figure, you can see the roll and pitch angles for the attitude, and the blue dots here are the output of the magnetometers and sun sensors, while our model, when the ambiguities in our model are fixed, or when we have the fixed solution through the array-aided POD or PAD, or precise attitude determination, we can have better attitude determination there. Also, when we have 4 antenna, it means that we can perform the array-aided precise orbit determination, which we received the orbital accuracy better than 5 centimeters, which is very good for LEO-PNT. So the next one, if we have a mega constellation of small satellites, so there are some solutions, some suggestion to improve the orbital accuracy, as I explained. But there's another way to improve it, which is calculating the precise ranges between all satellites. So if we can have everything there, in a ground station, and we start doing POD, calculate this precise ranges, and then we can predict the ranges for that one and broadcast the ranges to the satellites, we can apply something called relative onboard POD, and based on that, we can actually have the orbital accuracy at several centimeter level. So that is another concept that we have tested for real-time LEO POD. So that was mainly the the satellite side that can be applied no matter in dedicated LEO-PNT or in broadband constellation that can be considered for a LEO-PNT system based on the signal of opportunity. Besides that, we know that for the LEO-PNT system, we need to have also the positioning model, a good positioning model. And if we are talking about broadband LEO satellite as a LEO-PNT system, we need to have a good model to do positioning. What we developed is a Doppler shift-based multi-frequency, multi-constellation model, which is based on Doppler shift, and it's published recently in Navigation. And we have tested for the absolute mode and in the differential mode. It's validated through a simulation because we didn't have broadband signals continuously, and we know that the signals are not available in low elevation angle, and also there are some restrictions for the current broadband constellation to do not. And actually, we as a user don't have all the signals from all available satellites in our sky at the same time. And also, there is no multi-constellation receiver. So that's why we had to simulate the Starlink OneWeb Iridium constellation, and we did some tests. The outcome was based on the model, and considering that the satellite orbit of the whole constellation have sub-decimeter level of accuracy, and we can have more than one satellite trackable by a user, and a multi-constellation receiver is available to collect all the constellations. But we can have meter level and in the absolute mode, and decimeter level in the differential mode. So I mentioned it's possible if we have satellite orbits of the broadband constellation in the sub-decimeter level. So that's another question, because what most of us are doing is using 2-line elements and then We have two-line elements of the whole constellation. We are applying some error propagation, but we cannot reach to that sub-decimeter level easily. What we are working on right now is a network-based precise orbit determination of the broadband based on Doppler shifts. So I cannot explain because the paper is under review in GPS Solutions, but hopefully it will be published. Yeah. So as a conclusion, if we want to have a LEO-PNT system, if you're talking about a dedicated LEO-PNT, it's like having a GNSS in the LEO region, another GNSS, but in the LEO region, but with let's say with smaller satellite, with some challenges in terms of the processing budget, the models, the satellite constraints, and the sensor quality. So all of them should be considered. If you're talking about the broadband constellation, that is another issue because yeah, if we can receive all the signals, if we can apply the precise orbit determination, if there is a trust to what we are doing, that is another thing should be considered in the LEO-POD or let's say LEO-PNT systems. What we are doing is working on that part. We have a student who is working on spoofing a jamming part of LEO-PNT, and but there are many open areas based on my area of work, especially in the POD of mega constellation in real time, something that we needed if we want to have a LEO-PNT system. But there's another question. This question is related to, let's say, to the broadband constellation. If the constellation owners recognize this opportunity of having LEO-PNT system from a broadband constellation and are going to provide or expand their services and their revenue or not. So that was the question. So that is my talk. I hope you enjoyed it, and if you have any questions, yeah, feel free to ask.
Okay, good. So Amir, thank you. A very interesting talk. And yeah, we received a couple of questions and would like to forward those to you. So the first one was, you kind of explained this in parts already on one of your slides. So the first question was, what's the typical clock jitter in a LEO satellite, and are any ground systems used to reduce the clock drift?
Actually, that is depend on the type of the satellites. We have some. What we are usually using is we have some LEO satellites for remote sensing, which are equipped with ultra stable oscillators that are perfectly okay for most of real-time missions, including LEO-PNT if you want to consider such big LEO satellites. But for the small satellites, it depends. Again, it depends on the type of the satellite. So I cannot specifically mention for any satellite, but I can say for if they are equipped with orbit, let's say open control oscillators, that is the worst one.
Okay, thank you.